Oh, thanks, Jamie. Didn't even notice that. I was trying to say, I think that this is about the time when I'm going to usually start the recording for the class. But if you notice that I forgot to either start the recording or unmute myself, don't hesitate to say something. That'd never be considered rude. Appreciate it, Jamie. Oh, and I wasn't looking at the clock carefully. We've been ready to go for a few seconds there. Welcome back, everyone. I do have a few announcements that I want to start with today, but any questions or comments from folks right now? Okay. Well, if you notice that there's scribbles on the Moodle webpage, oftentimes this is just relative to a question that happened in class. So we were looking at one of the limits that I think folks have all seen in the homework, which was a little bit dicey to get through. What happens on this one is we still approach it as before. The highest power term in the denominator is t squared. And so on this step, we divide everything, numerator and denominator, by that t squared. The trickiest part is dividing the root t by t squared. The algebra looks about like this. Your square root of t has to be written as a power 1/2. Then the power 2 down below here, well, we need to make that have a denominator of 2. So power 2 is just as good as 4/2. And then ordinary work with the exponents from here on out. You subtract 1/2 for the 4/2, get t power 3/2. And that's how this all reconvened right here. So I think that was one of the nastier problems on the web assigned homework. There was several questions on this one. Any questions, folks, on getting through the first steps for this type of question? Okay. Well, the other announcements I have are nothing too major. Our first quiz number one is due today. That's the quiz. Let me clear this out for a moment. Right up here. And our goal is to get in the habit of always posting a new quiz on Wednesday of every new week. And that's where I have to give you full disclosure. I forgot to do my homework today. I think I'm just getting used to the ordinary rhythms of how class goes, so I'm not quite in a good workflow. I forgot to post. Let me get it to about there. There's where, oh, it scrolled on me. I forgot to post our second quiz. So we're off the hook on quiz two for this weekend. And I'll be sure to get into a normal habit of posting those quizzes. I may end up posting them on Tuesday since that's a less busier day. That way I won't just forget like I did on this Wednesday. So sorry about that, folks. Just one quiz, but we're still getting used to the rhythms of the class. Any questions so far, folks? Okay, well, looks like we can get started. The hardest thing about a calculus class, whether you're taking this one and a different calculus class, is always getting started, understanding what's going on with the limits. And so let's take a look at what we did in section 2.2 just to compare what's about to go down in section 2.3 that we started on Monday. So what 2.2 is really all about is what happens to your function in the long term. For example, if x is going off to infinity, then if there's a horizontal asymptote, the value of the limit here would be the same as the asymptote. So these limits are just all about is there a horizontal asymptote? If so, it tells us what happens to the function in the long run. And if we're going off to negative infinity, same kind of idea, except we're going off to the left. If we found that there's a limit of 8, then, as you saw in the quizzes that's due today, you also have a horizontal asymptote exactly at y equals 8. So that's the essence of this section, 2.2. But now we're turning it all around and saying, well, what happens if you're interested in stuff that happens in the middle, not on the edges, far right or the far left? And that's where this information is all about. If we take the limit as x goes to a, here the difference is there's no infinity. There's going to be an actual finite number, say 1, like in the example below. Then we're just trying to figure out what value does the function get closer and closer to as x itself gets nearer and nearer to the finite number a. If it approaches a limit, that means f of x can get as close to that value as we'd like by taking x sufficiently close to a on either side of a, but x never has to actually equal a itself. That is always something we come back to because it's just really subtle and tricky when we deal with this for the very first time. So in our example that we looked at here, there are two things that are tricky about this. If we calculate f at 1, let me take a temporary highlighter here. F at 1 is just asking for this value. The answer is the second coordinate of 1, and so we get that result. But if we're instead asking, what is the limit as x tends towards 1? So that computation there, well, we said the result is 2. It's not equal to 1 at all. The reason for that is, let's take a look at this in yellow. If x gets closer and closer to a in our problem is this value, a 1, on either side, well, what happens to the curve? The height of that curve is getting closer and closer to 2 on the right-hand side. And if we start off on the left-hand side, same issue. It's decreasing closer and closer to the height of 2. So we said that the limit is 2 down here. Any questions, folks, about that quick refresher? Okay, well, we took a look at how this one goes graphically. Example 2, we looked at 3 different functions that have really the same kind of ideas going on. We're taking the limit of this function as x approaches 1. Well, from the left, we're getting closer and closer to the height of 2. And from the right, we're getting closer and closer to the height of 2. So we said the limit was 2 on this one. And it turned out for every single one of these functions, the limit is actually 2. There's a little bit more going on here in this problem. So when we get to section 2.4, we'll take another look at this example and see what weirdness is happening here algebraically. I mean, the graphs all look about the same, except for a subtle difference right where these open circles or solid circles are. Any questions, folks, on getting through that example 2? I think this one was definitely tricky to look at. Okay, well, we're on our way to the new content. So next up, we need single-sided limits. This is where it gets a little bit tricky. We need to know what happens when x approaches a, but from a definite side. So take a look at that right there by the red dot. Give me a moment. Let me get an actual pen going. Let's go with this one. When you see that red dot, a with a negative sign, this means x is approaching a from the left. Likewise, if you see a plus right here, the a plus would mean x is approaching a, but this time it's coming in from the right. So all values larger than a is all x is allowed to take on. So let's say x is approaching a from the right. Now what we need here is a good picture to show what all this looks like. So here's going to be our example graphically to go along with this definition. Let me see if I can include just a little bit of extra space here. It's always kind of tricky on these systems, try to scroll to the perfect amount so we can see everything we want to see. Let me just move my windows just a touch. So we can get that scroll bar back. There we go. This mouse is a little too sensitive, I think. Okay, we'll leave it to that amount of zoom. And here's going to be our big example to show what's going on here. So we're trying to highlight both of these limits, this one and this one. I want to make this concrete, so I'm going to pick a number a. Let's make it be 2 or something like that. Let's go with a 2. I'll plot the function in blue for both of these. And right at 2, let's put in some extra tick marks. Let's go 1, 2, 3. We have a couple weird issues on this function. Let's say there's a solid dot here, an open dot here, and another open dot here. Now, my function, just a random example, is going to look like this. Swoops down and hits that point right there. Up arrow on the left is just to convey it's shooting up and towards the left in that direction. Oh, And let me actually change that up. Sorry about those working in pen. I wanted this one to come in towards the open dot. There we go. Next, when we pick up and go to the right of 2, let's let it come down here in this kind of way. And again, this is just a random example. I'll make mine shoot up again this way. What's really interesting is what's happening right here, right in the middle. And that's what these notes are all about. What happens with the local behavior? So we have 2 limits, and let's analyze both of them for this example. First, any questions about the definitions we see or the graph itself? Okay, well, let's handle this limit up here to start. And I should label my function just to be specific. This is y equals f of x. And let's take the limit as x approaches the number a, but our number a in this problem is going to be the 2 you see down here. So limit as x approaches 2. But we want to take it from the left of the function f of x. So analyzing this really carefully, first thing you need to know is that direction right there. So always watch out for any weird symbols that you might see. And Dexton says this should come out as a limit of 2. Awesome, Dexton, I agree with you. So when we see the 2 from the left, that means x is approaching a from the left. But in practical terms, my finger would be right about here, tracing along the graph. As we get closer and closer into 2, but only coming in from the left-hand side, where the red dot is, the height increases until it gets closer and closer to a height of 2, like Dexton said. So the limiting value on this one would have been a 2. Any questions, folks, with the first limit here? Okay, well, that was so fun. Let's try it all over again. Still, we're interested at 2, but this time we're looking at this limit down here, taking a right-hand limit. So this becomes limit x approaches 2 from the right-hand side of f of x. Most important thing, once again, is don't look just at the number, also look for a directionality. If there's no pluses or minuses, we have to come in from the left and the right all at the same time. But the plus here means we're really on this curve. We swoop around, get closer and closer to 2. Any volunteers for the limit on this one? Limit of 3. Yeah, absolutely. So another question Jamie asked, if we had to find the limit of 2 for f of x without a direction, would it be does not exist? Yes, that's absolutely correct. And that's pretty much what this problem is getting at towards. So theorem 3 is the next thing we're going to look at, where the left-hand limit, right-hand limit have to both come out to the same value if we're talking about this limit over here really existing. So let me put in the limit. The limit on this one comes out as a 3, as folks said. Visually, your finger would be doing this, moving towards 2, but only on the right-hand side, getting closer to 2. And yeah, height of the curve, it's approaching a height of 3 as we get closer and closer. So single-sided limits are a little bit weird because, again, this is always a bit of a trickiness we have to navigate through. Once you get a hang of it, it's just like anything else in math. You learn to look for these weird little symbols and signs that direct a certain type of limit versus another. Well, any questions, folks, with that definition too? Okay, and going on with the earlier comments about all this, we have theorem 3, which tells us if the limit as x tends to a of f of x equals L, that means it really exists. This can occur if and only if the left-hand limit or the right-hand limit both exist and they both agree the same exact number. Oh, that's a great question. So Doug is saying, what is the real context for something like this? I think we can get a pretty good one to put in. So going down below, single-side limits could be pretty hard or pretty interesting to imagine for something like this. like to watch things grow first. So for me, this is a pretty good way to think about these limits. Let's say this is t for time, going that way. And let's say this is y for population, size of something. I'm not too sure what the population should be. Let's imagine of crickets. So totally random example. I'm not sure what the right unit should be for the population size of crickets, but let's say it's all crickets in an area in Idaho Falls or something like that. And let's just put an upper bound here of maybe something like 10 to the power of 8 crickets. Again, I'm not sure if that's accurate, but it gets us started at least. So I have a tick marks, 10 to the power of 8. This would be 10 to the power of 4. And this is t for time. Let's say we're starting out in, sorry, I lost my red dot. We're starting out down here corresponding to 0, meaning January 1st. Well, the cricket size is going to be down here, pretty much flat. And as you go through, let's actually put some units here, January. Thinking in Idaho again, if you're somewhere out here in maybe March, maybe that's about when the crickets start actually increasing in population size. They begin hatching as the ground thaws, things like that. I'm not an expert on crickets, so maybe that has to be May or something like that, but let's keep on going with that. So something happens in March. Let me put in some better symbols here. I want a solid dot there to say population 0. I'm going to overline the axis to say it stays at 0. But with the open circle here for March, because in March something happens, the crickets wake up, takes on the value, and let's just say it starts growing like this. So this could be something that you'd be analyzing in, say, a biology context. And now there's two really interesting limits on this one. Let's write them both out. You might be interested in the limit as t approaches. I put March here, but let's maybe put down a number. So it's January, February, March. So let's say here, let's put down a 3. So that's just conveying months. So let's take the limit as t approaches 3, coming in from the left of, we need a name for the function. Let's let it be y equals p of t, population size at time t. So if we took this limit right here, any volunteers for what this one should come out as if it's 3 coming in from the left? Yep, absolutely. This should be a 0 because as we come in from the left, the height of this curve representing the cricket population stays 0 the whole time, never changing. So this would be a 0 here. Likewise, the next related limit would be limit as t approaches 3 from the right, so 3 representing March once again. Here we're coming in this direction, and the population settles down to 10 to the power 4, absolutely. So limit on this one is 10 to the power 4. So maybe not the best quick example, but that at least makes it a little bit more concrete for what we're doing with these kinds of things. Glad that helps, Doug. Other questions so far, folks?
Real quick, I think I have a question.
Yeah,
Um, Pertaining to the one above the crickets.
this one
So
here.
yeah, I understand like how you get 2 and 3, but how do you get those points, like the open circle points? Where do you like know where to put them?
I just pretty much invented them at random. So this would
Okay.
change from problem to problem. And I think the only reason I put a solid dot there was I just wanted to show as a related example that if we want to calculate f at 2, that one comes out as a 1. So it's possible to have your limits different and even the function value different. But in the end of the day, yeah, these solid dots and open dots have to be arranged in a particular way. If you're doing an example like this one. So here's where we're going to show how do we line up our open dots, solid dots, and those kinds of things for this kind of exercise.
Mhm.
But everything else, they'll either be missing or say like on, oh, even this problem, they are supplied.
Okay, so they should give you that that information on different equations, basically.
Yeah, absolutely.
Okay, that makes more sense.
Awesome. Glad to hear that. Other questions at the moment? In this problem, oh, let me double check. Okay, yeah. So that's a great question, Eli. What makes the f at 2 equals 1 on this one was when we input a value of 2, it's that solid dot that says this is the actual function value we're taking on, a height of 1 over here. So if it's just the function, you're looking for a solid dot or a place where the curve actually hits. So f of 1 would be up here. That one looks like it'd be about maybe a 1.5 approximately. Does that make sense on getting that value, Eli? Awesome. This is a pretty tough definition to crack open, so I absolutely appreciate those questions. Any other questions or comments at the moment? Oh yeah, absolutely. We are only just about ready to get into that one. So any questions before we get into Theorem 3? Okay, let's get into that one as Macy was saying. So this limit is kind of a different, or this theorem is kind of a difficult one to really process, but it's good to see it through example. So let's pull down this example temporarily. It's hard to get a good screenshot here, but that'll do the job. It's a little bit cut off on the f of x part. I want a screenshot that goes to here. Let's make this one our example that corresponds to Theorem 3. Well, you know what? Let's make our brand new example. That one's getting a little too busy. I think it'll be easier to see this one if we just make up a brand new one. So here's a situation where a limit wouldn't exist, and we could use Theorem 3 to really address why. Let's take another value, maybe at -1, -2, -3. At -3, the function is going to have a break. Let's put in maybe some values here, 1, 2, 3, -2. So this one's going to start at -2 with a solid dot going this way. Let's make it go down linearly in that direction. And when we come off to the right, now here I have to be careful. I actually have to put an open circle right here, because if I put a solid dot, I'll fix that in just a moment, this would fail the vertical line test. This would no longer be the graph of a function. We can't do any limits or any calculus at all, because a vertical line comes through and hits 2 points on this graph. It's no longer the graph of a function. So one thing you'll always notice is if we have open dots and solid dots, there can only be one solid dot in any vertical line that goes through, so that we truly have a graph of a function that obeys the vertical line test. But once we get there, the function does, again, just a random example. Let's let it do this. So looking at this problem right here, the A we're interested in all three of these limits, is going to be that value. So let's take a look at two different limits. Let's say, well, three different limits really. Let's take the limit as x approaches -3 of f of x. And I should label the function. Let me just throw it here on the graph, y equals f of x. Well, this one's kind of tricky in a way. Anyone see what the best answer might be for that limit? If we're not sure, that's the content of Theorem 3. So let's work through Theorem 3 now and just leave a question mark here. So it says the limit equals some number. We're going to see if we can resolve that. If and only if the left-hand limit equals some number and the right-hand limit equals some number, and those both agree, they equal the same value. So let's first work on the left-hand limit. Limit as x approaches -3, and we'll do it from the left of f of x. What would you all say this limit should come out as? Absolutely. This one, for approaching -3 from the left, we're on this part of the curve. It increases without stopping and approaches the height of -2. Because of the solid dot there, it actually hits the height of -2, but that's not necessary for the limit to exist and equal -2. That just has to be a number it's approaching. So this one gives us -2. Next, if we take the limit as x approaches -3, but this time from the right, so a plus sign, we have to put something inside the limit. There's the function f of x. Well, in that case, that limit's different. We're approaching from the right, so we're going up this curve, and it's a gentle increase until the numbers get closer and closer to a height of 3 this time. So now that's what this content is all about. In mathematics, we have some really severe problems. Anytime there are multiple answers, it means that mathematics gets a little bit more dicey. We have to work a lot more harder. So when we define things in mathematics, like a limit, we want one unique answer for that thing, or else we'd say it does not exist. So what's the limit as x approaches -3? Well, it depends, right? If you approach it from the left-hand side, we found -2. If you approach it from the right-hand side, we found +3. But because these two do not agree, we would say that this limit up here does not exist. So to put, either does not exist, if you prefer to write out, or you could just say, as what was said in the comments earlier, DNE is a great way to say it as well. So that's the content of this theorem. If you did put a number here, if you said that the limit was something like 1 or 2, then we have to get 1 and 1 here both at the same time. Does that make sense to folks with the content of that theorem? Awesome, glad to hear that. Again, it is pretty tricky, but in the end of the day, this is a picture of what it looks like when an ordinary limit, the ones we are studying at the top of these notes, fails to exist. So if you see something like that by the red dot, we're approaching a number, and that number matches whether we're coming in from the left-hand side, the left-hand side limit, or the right-hand side, doing that right-hand side limit. And the moment you get different numbers here, we just say, you can't put a number there, it does not exist. But you'll also notice if you're doing this through a graph, that's the telltale sign, there's a whole jump in here. We're going to look into issues about continuity. This is in section 2.5, but for the moment, it's not a bad idea to start thinking about these things. This whole situation right here is referred to as a jump discontinuity. The naming scheme makes sense. The curve goes here, and then it jumps up and carries on, and that's what makes it the discontinuity of a jump type. Well, that's what's going on with Theorem 3, and because there are a lot of ideas, I try to always kind of pause a little bit as we see new content and try to do a related example right away. So that's our example 3. Any questions at all first about this information here? Okay, now carrying on down, here's our example 3, where we're just going to kind of do the same sort of information all over again. It's a pretty good review problem in its own right. So it says use the given graph of f. That's the graph here that we see in red. This is kind of a dicey screenshot. I'm going to try to make sure that the picture quality is a little bit better for future examples. Is everyone able to read that okay at the moment? Okay, glad to hear that. If anything ever comes out just weird or broken, just please let me know. I'll try to get it resolved one way or another. So here's our graph of the function f. We want to state the value of each quantity if it exists. If it does not exist, explain why. And with these kinds of explanations, you don't have to go into any great deal of depth. In fact, you could just really cite what's going on with these limits right here. So we'll rehash theorem 3 as we do this problem. So let's go off left to right, top to bottom. First limit is, well, being very careful, it's a single side limit. It says x approaches 2. That part right here where it says approaches 2 means we're looking here on the x-axis. But that negative sign as where you would put the exponent says we're approaching 2 from the left. That means our curve that we're interested in is this side. And as we go closer and closer to 2 from the left, the height of that curve gets closer and closer to a value of 3. So we would say on this one, equals 3. You'll notice we've done a lot of these examples where you just look at a graph, read off the limit. That means there's a good amount of these in the homework, and you can expect in section 2.3, exam problems will look like this as well. Any volunteers for what should happen to that limit there by the red dot? Eli says the value comes out as a 1, and yeah, absolutely. Notice here with the limits, whether there's a solid dot or an open dot, totally irrelevant. It doesn't matter what happens right at 2. All that matters is, as you get closer and closer to, let me say that again, as you get closer and closer to the number 2 from the right, the height of this curve, tracing it down, gets closer and closer to a height of 1, as Eli said. So the limit here is just 1. So that's interesting. Next, we want to know the limit as x approaches 2. I'll leave this one up to the class. Anyone see what we should put down right here? Emily says DNE. I agree. And honestly, when I'm doing this as my own personal work, that's the acronym I use as well. Does not exist. And why doesn't it exist? Well, there's a break in the curve right here, so that's a good indication. But also, when we took the limit as we went to 2 from the left, we got 3. As we went to 2 from the right, we got a 1. Those limits don't match. We need to give an explanation, but we can just simply say does not exist, since lim x approaches 2 from the left of f of x equals 3, lim as x approaches 2 from the right of f of x equals 1. If this is all you say, then to me that's a total explanation. It means you couldn't put a number on this one because there's 2 candidates. It's either 3 or 1. In other words, the direction mattered, and that's what forces a does not exist on the entire limit here at 2. Any questions at all, folks, on this third part right here? I think that's the trickiest of this set. Okay, well, although this one, in my opinion, is the trickiest, I think the rest of them are still tricky. So let's go through this one carefully. This is kind of a review. It's not anything to do with limits, but it's still tricky. If you're calculating f of 2, this is essentially what my fingers would be doing on the page. Oh, let me hit the chat first. Absolutely, we get a height of 3. You take the 2, go here on the x-axis, and you move up until you hit the curve. Notice that open circle there. That means you pass through the curve. You really land here at the value of 3, as Dexton said. So this one takes on a value 3 altogether. Does that make sense, folks, on the function evaluation? Okay. How about this one, the limit as x tends towards 4? Yep, that one will hit on a value 4. And notice this curve does have a hole there. It's a discontinuity, but it's not like this one where the whole curve jumped downwards. So if you approach from the left, it gets higher and higher, closer to 4. And as you approach from the right, it gets higher and higher, approaching the value of 4. That's important because this one didn't have any specific directionality. We have to be getting closer to 4 on both directions this time. That does in fact happen, so we get to say the limit is 4. Only one last thing to get through. How about the function value at 4? Anyone see what we should put here? Absolutely. There's a problem in the graph, right? There is no solid dot for us to get through. If there's no solid dot, you can either say does not exist, undefined, any of those kinds of descriptions would be just fine. I like does not exist. It's a good acronym. I'll put here undefined, only because that's something you would typically say if it's a function value, and does not exist is something you'd more often say if it's a limit. But that's a stylistic choice. You could say undefined on both. You could say does not exist on both, and we're conveying the same information. Well, we did, folks. That's a pretty typical problem that you might see in the homework. This would have been a typical quiz problem if I remembered to post that quiz. Sorry about forgetting quiz 2. We'll get back on the quiz schedule on week 3. And if this was an exam question or an exam we're doing on section 2.3, you could see problems about like this. It's all about knowing what happens with the limits graphically. Limits are pretty tricky on their own, but if you have a mental picture of what does a limit look like when it doesn't exist, like this one, what does it look like when it really exists, like this one, then that makes it so much easier to really work with the limits and the formulas we're going to see in section 2.4. So 2.3 is all about graphs. In 2.4, we'll use the limit laws to actually calculate these things when the graphs themselves are missing. Well, any last questions, comments, or concerns, folks, before we try some more concepts on these notes? Okay, well, as you can see on the scroll bar, if you're paying attention to that part of the document, we're about halfway through the notes. Now we're getting to something involves infinities once again. Here, that gets a little bit vague because we have seen limits involving infinities, but this is a little bit different. So the thing to take away from here is this time, the infinity is in the output, either a positive infinity or a negative infinity. Let me bring that up just a touch. Whereas in the prior notes, pause one moment here, let's take a look at the Moodle page. This had a limit on the input for x itself. So whenever this occurred, we were getting horizontal asymptotes. Say on this graph right here, we took the limit as x goes to negative infinity, found a horizontal asymptote, but now we're putting everything on its head and saying, well, what if you went to a finite number, but you got an infinity? This is now giving us vertical asymptotes as opposed to the horizontal asymptotes. But these are very tricky limits, so let's first put down a picture. Let's see, let's put maybe 2 different values. It says as x approaches a, but we need something concrete to get a feel for this. So for the first a value, let's let this one be, how about a 3? For the a value down here, let's let this one be a -1. These both say we hit values of infinity in our answers and different kinds of infinities. That once again implies there must be a vertical asymptote. And by the way, this is finally tying back to questions that we had all the way in section 2.2. So that's very exciting. The folks that understood that vertical asymptotes might enter the picture at this stage were really looking ahead. I think that's pretty cool. I haven't graphed anything just yet, but let's put down the actual curve for f of x. Let's let it go this way. Looks like a typical kind of function you might see in a pre-calculus class. Let me try to make it a little bit nicer on the right end. So that's my graph. It comes in 3 different pieces, but all of it is one total function, y equals f of x. I want to look at several limits on this one, focusing on the ones where we could get one infinity or the other. So first, let's take the limit. As x approaches -1 of the function f of x. As you approach -1, from the left, the function values are getting higher and higher, and there's no stopping. The up arrow says you can get as high as you want on this graph just by getting closer and closer to -1. If you approach from the right-hand side, it's also getting higher and higher without stopping. So we would just say the limit here is infinity. Does that make sense to folks so far? Okay. I would say for an example like this one, it's not as easy to get a good concrete example like we did with the crickets on an earlier example, but you can still get something good about this. When in the real world do you see infinities show up, weird things like this? You can think in terms of cosmology if you're into that kind of stuff. What's happening with black holes? You have a lot of mass where the density is getting higher and higher. And as that happens, we have gravitational forces getting larger and larger, tending off towards infinity. So there is no limit to how much gravitational attraction you get within a black hole. And these are the kinds of limits that start to come out in physics. From a different point of view, if you take the limit as x approaches, let's make this one be the positive 3 of f of x. Well, as we're around positive 3, the function is also in a certain sense blowing up. The values are getting very, very large negative or just plummeting down, both on the left side and the right side. So this time we would say negative infinity on this graph. So those are the two new kinds of limits. Again, we stumbled upon a couple of these when we were in section 2.2, but now we get to formally define exactly what we mean when we put infinity here or here. Any questions so far, folks, at the moment? Okay, then once again, when we were in section 2.2, let's pause for just one moment on this screen. Just to reiterate, if you had a limit where x approaches one version of infinity and it's finite, you had a horizontal asymptote. But flip it all around, if your infinity is on the output, like say over here, and you were heading towards a finite number, that means you had vertical asymptotes for sure. Let's see if we can squeeze them on the graph right here. There's a vertical asymptote going this way. We don't say y equals any longer because that's horizontal. To make it vertical, we go x equals -1, x equals 3, and these are the vertical asymptotes. So if you head off towards a finite number, but your output is infinity, then just take that number, -1 or +3, and you have your vertical asymptotes immediately. In fact, let me see if I can fix the color coding here just to connect the dots on that. -1 coming from the first limit there, and +3 coming from the second limit over there gives us those vertical asymptotes. If you already know you have vertical asymptotes, then once again, the limits are just put in with either infinity or negative infinity. Well, that's a lot of graphs so far. Any questions at all, folks, on these two new concepts here? Okay, and after looking at a brand new definition, we've got to have an example. I think it's just another graph one, and here it is. It's also a reminder of what we were saying before, that the line x equals a will be a vertical asymptote of the curve y equals f of x if at least one of these things has to occur. The major thing is you had to get an infinity. Notice the different ways you can get an infinity. You either approached a, or a here for positive and negative, or you approached it from the left, or you approached it from the right. So if any one of those limits occurs, and on each one of them, it's the limit as x approaches a, then x equals a has to be a vertical asymptote, like we were seeing in the prior graphs. So with that in mind, example 4 is just another one of those graphical computation problems. Let's do this one as a class and see what we have. First, it says limit as x tends towards 2. Any volunteers for the value of that limit? Macy says negative infinity and absolutely. So here's how I would think about this one. Starting off when you read the problem, if it says x approaches 2, that means you come over here and you're interested in when x coordinate itself is 2. Now, this is a double-sided limit. There's no pluses or minuses around that 2. So we have to have behavior that matches on both the left side and the right side. But looking at the curve, yeah, it's just plummeting down to negative infinity on both sides. So we come back here and just say negative infinity because of that portion of the graph. I'll delete all these arrows in the moment, but that's kind of my stream of consciousness, how I even think about the problem. My eyes go here, they grab the 2 on the horizontal x-axis, look at the function values, and if they're plummeting down on both sides, that would be your output, negative infinity. Let me get these off so it doesn't get too busy on our graph. And let's just try it again. If x approaches 5, we're here on the graph, and absolutely we'd get infinity on this one. But notice on both of these, those are the double side limits. Give me one moment. I had a pop-up that said something was corrupted. I don't know if you saw that on your screen. I'm just going to save it just in case. So on both of these are double side limits, but this one is single-sided. Oh, question first. Macy says, so if the other side of 2 was infinity, would it be a does not exist? Yes, absolutely. Here, if we had on 2, if maybe this portion of the curve didn't exist, and it was going up like that, well, we couldn't say negative infinity because now it would depend. It would be either negative infinity or positive infinity. Best answer in that case is does not exist, like you said. Other questions at the moment? Okay. Well, looking at this one, it says x is approaching negative 3, so we're here, but we're coming in from the left, and absolutely, that one would be negative infinity. Coming in from the left means you're just tracing down this curve. You're tied to that track. You're going down and down without end, so negative infinity on that one. Then finally, one last one, negative 3 from the right. You're really just on this curve going up higher and higher. So that one would be a positive infinity. And really, it's kind of just a rehash of what we were looking at before on our prior graph that we hand drew. But now we get to state the equations of our vertical asymptotes. Really, all we need to look at is where did we get our infinities, much like we were seeing up here. And once you find the infinities, grab the values x was approaching. So x approached 2, 5, negative 3, negative 3. That means the vertical asymptotes are x equals 2, x equals 5, and we only have to write down x equals negative 3 once. I'm going to take these off so it doesn't get a little too busy here. But does that make sense to folks on how to read the limits or state the vertical asymptotes? Awesome. I'm glad to hear that. Again, this is not a whole lot of applications on this one. This is just us getting used to reading out the limits. We'll see a little bit more concrete applications when we're in the section of 2.4. Macy asks, will we have problems where it asks for both asymptotes? I think that would be a possible question that could come up. So I'm glad you asked that one. If it were asking for other asymptotes, the wording would have to change here. It might say the equations of all asymptotes, and I'd have to be very specific on the wording. I probably would capitalize all or put all in bold or something like that. So that equation is possible. And because of it, let's say also state the equations. That's a bad cue. Let me start again. Equations of the horizontal asymptotes for that kind of question there, we need a different sort of limit. We'd be wondering, what happens as x approaches negative infinity for the function, I was going to say f of x, but this is an r function, so r of x. On that limit there, if we're going to negative infinity, that means we just care about the far left end of the graph. And it looks like the height of the curve is getting closer and closer to a 0 on this one. So we would say y equals 0 just from that information, but there could be more. So we would also have to take a look at what happens in the limit as x approaches positive infinity now of the function r of x. That means we're only concerned about the right-hand side of the graph. At positive infinity, we're tracing down this curve. And keep in mind also that when we produce a graph, we're assuming that we showed all of the relevant behavior. So if it looks like it's settling down to a height, we can assume that that behavior carries on. So it looks like the limit is 0 here. And same horizontal asymptote. We'd only have to write it down once. So if other asymptotes come into play, we only have a horizontal asymptote if x is going to positive or negative infinity, giving a finite number. And we're only getting a vertical asymptote if x approaches a finite number, but the output is either positive or negative infinity. Again, that's a lot of information to keep in mind all at once, but the homework kit will help quite a lot when you see these problems again. Any other questions or comments, folks, on this example here? Yep, you betcha. Thanks for these excellent questions, folks. Well, I think we're just about done with these notes, but I did have a promise of a slightly different kind of question, and that's this one right here. And full disclosure, I think, in my opinion, that this is a pretty tough question. We might make this one our second quiz when we come back next week, doing something along these lines, maybe not as much information, but something similar in spirit. And the idea with this is it's not too different from doing this problem, except in this problem, you had to produce the limits for a given graph. Everything here is now opposite. We know the limits and we wonder, what is the correct graph that has all that information and a function value looks like? So sometimes the best way to really internalize all this information and really know it once and for all, have it down pat, is if you can do it going backwards. So in my opinion, this is a challenging problem. So we'll take our time with this one. I think we have only one more example after these notes. So after this, we'll be in section 2.4. First, let's give this a try. It says, sketch the graph of an example of a function f that satisfies all the given conditions. There are the given conditions here. It also says in bold, your graph must pass the vertical line test. We touched on that, but let's be a little bit more specific right here. Let's put in a quick example of what we mean by passing the vertical line test. I guess we could say here, y equals f of x represents a function if and only if every vertical line intersects the graph at most once. So we want to write a graph that conveys that information. It's so critical because if it does not pass the vertical line test, then that would mean that you're not looking at the graph of a function. And everything we do in calculus requires that you started with the function in the first place. So let's do two examples on this one. I'll do the function in blue like we've been doing in these notes. My first function goes like this. Looks like it could be some kind of polynomial function. Even degree since the arrows are going up. And my second function on the right-hand graph looks like this. Starts off nice. At the moment, it looks like a function. But the moment I double back, come in around, now I've got a problem. But let's let that curve stand. So on the left, this one is a function because every vertical line, no matter where you place it, say here, it'll intersect at most once. So on this one, we would say passes the V for vertical line test. What's the punchline? This is a function. Now, this curve is a little bit strange. It might be really interesting, but because of a single line coming through like this, hitting the graph more than once, it hits here, here, and here, this fails the vertical line test. So the punchline to this one is, this is not a function. So that's our goal with what we're trying to do in example 5. We want one function, meaning our graph must pass the vertical line test. The graph could come in pieces. It could be something like this, a whole bunch of different segments. But you'll notice on every one of those graphs, they always pass the vertical line test. So same idea, we'll try it down below. Any questions at all, folks, with that quick demonstration of what we mean by vertical line test? Okay, so here's the example next. It says sketch the graph of an example of a function satisfying all those properties. Ensuring it's a function just means it passes that vertical line test we discussed. And this is how I'd probably start off every one of these problems. Just give a big XY axis. I usually make my x-axis a little bit longer just to separate out what all happens on these different inputs for x. Vertical axis goes like this. Another thing to mention here is there could be more than one different graphs that satisfies all this information, and it's totally correct. So that's why we said an example to mean there's more than one correct answer to this kind of problem. There could be as much correct graphs as there are people in Zoom right now. There's 18 of us. It just has to nail down certain things. So I'll do the function in blue, but let me temporarily highlight like this just to show you where I'm focusing on. The first one's a function value. And whenever you see a function value like 0, 3, all you're doing is putting down a point. So let's go right at 0, up at a height 3. There's our point. It has to be a solid dot to convey that's really a point on the graph. And then from there on, I don't know what the curve does, but we'll start connecting the dots as we get through more information. So that's our first thing to navigate through. See if I can zoom in just a touch here. Next one is going to be a limit. And it says as we approach 0 from the left-hand side, our height has to be at a height of 4. So because of that 4, let's put in a tick mark up here. Next, it says as we approach 0, that means we're on the x-axis, heading towards 0, right where the origin would be. But as the x-coordinate gets closer and closer to 0, the height must be getting closer and closer to 4. What we now must put here is an open circle on the graph. And your curve can be coming up and in like this or down. It just has to approach the height of 4. I'll make mine come in about like this. The open dot right here by our red dot is critical because if we had both of these solid, that would be an automatic failure on the vertical line test. The graph would have an intersection here and here with a vertical line. So that's our first limit. Does that make sense to folks on how we're getting these pieces of the curves drawn in? It would matter on this one, it turns out. The question was, does it matter which one is open and solid? The only reason that this one had to be solid here was simply due to the function value. So that one actually kind of nailed down that solid dot in this case here. Other questions about that? Okay, well, let's turn it around and look at this limit. We're going towards 0, just like on the prior one, but this time it just says from the right-hand side. That means we're drawing in something coming in from this end. and we have to approach a height of 2. So we go over to 2. As before, we need an open circle right over here. And the curve, I'll draw it in coming in just like that. Again, the way you draw your curve is completely up to you. Some people might have done a horizontal line coming in or a squiggly line kind of as we're doing. Whether it comes increasing upwards, decreasing downwards, totally up to you. Just has to fit that limit there. So that limit there gives us this shape with another open circle. Now looks like we have 4 more limits to get through, but any questions at the moment? Okay, let's change the focus next to that new limit. Oh, first a question came through. Oh, gotcha. Thanks, Doug. So this one says we're heading off towards negative infinity. That just means we're way out here on the far left-hand side of the graph. But it says as you go to negative infinity, the output on this one is negative infinity. What does that mean? Well, there's no vertical asymptote. The only way you could get a vertical asymptote is if that was a finite number, like -6 or something like that. So going towards negative infinity and having a result of negative infinity, all that's telling us is that your curve is going down. I'll convey it that way. So that's how this portion here, the limit and the graph would be conveyed. You don't have to have the arrow, but I like to put that on there just to convey, keeps on going down into the left in that kind of direction. Here's our next one. We have information occurring at 4, so we'll go to the x-axis, just throw in 1, 2, 3, 4. And noticing at 4, well, we have infinities coming up. That suggests we probably want to put some dashed lines for a vertical asymptote. Again, this one had no vertical asymptote, only because x was going towards negative infinity, not a finite number. But now if you have infinities, where there is a finite number in here, that's when the vertical asymptote will occur. So it says as x approaches 4, but coming in from the left-hand side, f of x takes on values that are getting smaller and smaller, heading towards negative infinity. So 4 on the left-hand side is out here. I notice this is why I don't draw too much of the curve. I only want just a little bit until I read the next limit and know what to do with the rest. The rest is make it plummet down in that direction. So that's how these portions convey. Does that make sense to folks on that limit there? Okay, well, moving over to the next one, same kind of idea. We still have stuff happening around 4. Only difference is it's now going off to positive infinity. But that piece of information is still important. We're talking about only as x approaches 4, exclusively from the right-hand side due to that plus. So if it's from the right-hand side, that means we're on this end, heading towards positive infinity. I'd probably just draw a short segment and go up like that. So that's how the graph and the limit relates on these two right here. And it's always good every time you draw a little piece of this, double check. Are we still passing the vertical line test? And if I read off what's happening here, well, it says going to 4 from the right should be positive infinity. It should match up what's here as well. So double check for consistency as you go. Not a bad idea for these problems. Last one on the list is this one. It says as x goes to infinity, we hit a finite number. Now, that means there is an asymptote on this one. This one's going to be a horizontal asymptote. It's at height -4, so let's drop down 1, 2, 3, 4. I'm only going to draw the dashed line going to the right because the limit right here is for x going off to positive infinity. So we're only concerned about that right direction. So if x gets larger and larger, the function values get smaller and smaller until they're at -4. So I need to make this curve right here turn around and come down again, but then settle and start going off in this direction. So finally, that's how these two portions connect. And that's our entire total graph. If you're like me, this probably feels like quite a lot when you're doing it the first time. But if you're not sure if you have the right answer or not, what you could do is take all of this right here, get rid of the information, scroll down and just say, well, what is f of 0? What's the limit as x goes to 0 from the left, from the right? In other words, redo this portion with the right-hand sides taken out and see if you get the same information just by reading the graph. In that way, you'd be doing a problem essentially like this one in the normal way, and then just double checking your answers, seeing if they line up with all that given information. Well, there's probably more things that we ought to say about this one, but any questions or comments so far? The y equals f of x is optional. I just like to get in the habit of putting that there. Okay. Well, maybe one other thing we could put here. I'm going to use the orange pen just to convey. These are extra comments, not things you would have to put on a real quiz. But there are asymptotes on this one. For example, going this way, that's the horizontal asymptote, y equals -4. If a horizontal asymptote exists, we expect to see something like this one right here. Or more importantly, we should have something going off to either positive or negative infinity with a finite number. That's what gave that horizontal asymptote. Let me put some more dashed lines here so it just looks a little bit more normal. This one's a vertical asymptote, x equals 4. And for a real vertical asymptote to exist on your graph, that means x has to be heading towards the finite number 4. We see it here and here. And there must be infinities, one or the other. So that's what gives those two asymptotes, one vertical, one horizontal. Actually, rather circle the infinities there to convey that. There we go. Well, we did it, folks. That's the conclusion on that problem there. Any last questions or comments on getting through this one? Macy says, would 0 be an asymptote if the solid circle wasn't there? It wouldn't be an asymptote unless we had something like, say, let's take out that solid dot just temporarily. Oh, that's a Control Z on that one. There we go. So if we took out that solid dot, we still wouldn't have a vertical asymptote unless we had something like this going on. The curve right here would have to shoot upwards towards positive infinity. But then the thing that this would break is that limit right there. As we went to the left, we're no longer getting a finite number. We would be getting infinity over here. So that would be the only way to get a vertical asymptote on this location for a 0. One limit or the other would have had to have been an infinity. You bet you. Thanks for that question there. Other questions at the moment? Let me bring the graph back to its original. Gotta love Control Z. That's really helpful, it turns out. Okay, well, I just have one more example for us for the day. That's our example number 6 below. It comes with a big remark, and the remark is all about, this is more of a connecting example. This is what connects everything we did with graphs with what we're about to do in section 2.4, using the limit laws again to do these same kinds of limits. So that means we're only going to do example 6 once, essentially. Once in the notes, once on the web assigned system. It's probably not going to be a quiz problem nor an exam problem. Think of this as really just a demonstration. It says on the example, guess the value, and already that sounds weird. Guessing in mathematics is a weird command, but we're still going to do it. Guess the value of a limit, if it exists, by evaluating the function at the given numbers correct to 6 decimal places. Ouch. It is a bit tedious, and I did assign one of these in WebAssign, so I felt like we ought to do one as a class just so that it doesn't feel like I'm giving you a bunch of tedious busy work to do. We'll do the busy work ourselves as well on this one. Well, it's a little bit tough. We want the limit of that thing. We don't have a graph, and that's what we've been relying on. But we still have a calculator, and this is definitely a calculator type of problem. Let me open up Desmos real quick. I need to remember to do this before class. I'll get there in a normal kind of workflow. Okay, so I have a calculator going, and if you're using an ordinary calculator like a real one, you would just be plugging in 2.1 here, 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 and cranking it out. Honestly, it's pretty tedious, and you've got to get that in perfectly. So I would also encourage a different way to approach this one. Instead, if you have a calculator like Desmos, you can just input the function. So let's type that out. F of x equals. So if we're using Desmos to get through this problem, that's another indication. I'm not going to ask you this one on a real exam. It's too much busy work. And this is really a great one for a shortcut, just defining the function, which you couldn't do on an exam anyways. Get the fraction in, and it's x squared minus 2x. Down below, it's x squared minus x minus 1. And we're taking the limit as x goes to 2. So we're really, really concerned of what happens around here as I get closer and closer to, oh, I should zoom out a bit, closer and closer to an x coordinate of 2. Oh, it's actually over here. Should have read the graph. There it is. Well, we have a point there to 0. So as x gets closer and closer to 2, we're expecting an output of 0 just by our training of reading the graphs. But this problem is more about computation. It's asking us, what if there wasn't a graph and we had to do it just by looking at function values? Let's first say, what happens to f at 2.1? Again, in your calculator, you could put it in this way. 2.1 squared minus 2 times 2.1. Really, this is just a demonstration. We're going to take a big shortcut on this one. Divide by 2.1 squared minus 2.1 minus 1, and that would be the result there. But honestly, that's really tricky to calculate, and if I had to do that 6 times, I'm probably going to make a mistake just fat fingering typing the keys in wrong. So here's another way to approach it. Let me leave that there in case folks were looking at that. Just put in f 2.1 with the function evaluated or defined above. It gives us a really fast evaluation here. I need 6 decimal places, 0.160305. Then pretty much just rinse and repeat on this. Next one is at 2.01. So just throw a 0 in there, and that's the next function value. Notice the functions are, or the outputs to this function are getting smaller. This time it's a 0.019513 if we're rounding. And this is a lot of digits for me to try to convey. Let me know if I get any of these wrong. 0.019513 upon rounding. Next. Now this one's getting extremely close to 2, so throw in another 0. And just the output itself is getting closer to 0. This time it's 0.001995. Any questions, folks, with those function values there? Okay, well, that was so riveting. We'll do it all over again. Remember, this one is a double-sided limit. It's limit as x approaches 2 with no information on the left or the right. So these do look like they're heading towards 0, but that was from the right end. We need to double check, are we still heading towards 0 from the left end? Otherwise, the limit would not exist. So this time we're putting in a 1.9. Function value on that one is negative 0.267605. Should better double check those. Really easy to get these numbers wrong. 0.267605. Really, this would round to a 6. So for rounding, I'll put in the 6 there. Next evaluation is 1.99. So now we're getting closer and closer to 2 from the left-hand side. And, well, this was negative. This is still negative, but it is getting closer to 0. Negative 0.020513. 6 digits is a lot for me to memorize towards the end of class, but I think we're just about there. I need to remember that. I think I asked for 6 digits in the homework too. That's why I made it tedious here as well. But here's our last one. Getting still closer, 1.999. That's because we're now very, very close to 2 on the left-hand side. We get this value. Now, again, this one's really close to 0, negative 0.002005. So by the information we see here, again, we're going to guess the value. Any guesses from the class on what this ought to be if you had to put just one number now? It is a weird set of instructions, I have to admit, when I say guess, but pretty much what I would say on this one is if the numbers look like they're heading towards 0 on both ends, then, as Dan has said, our guess should be, looks like this one is also heading towards 0 as well. So that's what this problem is all about. We're thinking about what happens to limits when there's no graph provided. Well, this is just a connecting example. When we come back next week, this is going to be next Wednesday. We have Labor Day on Monday. We'll see how to do this all with the limit laws, not doing this kind of stuff and having to guess. Well, sorry, folks, it looks like I went over a full minute. I'll try to refund them back to you next week. Any questions at all before we call it a day? Let me double check that for you. The exam is going to be, let's see, yes, Wednesday, September 11th. As we're getting closer to that one, I'm going to start putting in more information here. Other questions so far, folks? Okay, well, have a great evening, everyone. Again, I get back on at 3:30 for office hours, so if you have questions, please feel free to come on back in and I'll be happy to help. I just keep my Zoom open, so if for some reason it closes out to inactivity and you don't see me in there, just hang out in the Zoom meeting. I'll pop right back in. See you folks later.